Reaction mechanisms. The mechanism shows how the process is thought to actually occur. The reaction may occur through a single step, like the rearrangement of methyl isonitrile into acetonitrile, or by a series of steps. Most reactions do not occur through a single step for several reasons. First, the energy considerations may be such that it requires too much energy to occur in a single step. It may be that there are a number of bonds that need to be broken for the reaction to occur, and that breaking them all at once would require so much energy that few collisions would have enough energy to react. For example, the hydrogenation of ethine with a triple bond between the carbon atoms. It requires a lot of energy to break the entire triple bond, but much less energy to break only one of the pi bonds at a time. Second, it may be that the orientation requirements for a specific molecule make it difficult for the process to occur in one step. But if part A happens first, then part B can happen more easily. For example, many organic molecules are large and complicated molecules, where the pieces that need to react may be buried in a larger clump of atoms. Breaking some bonds may allow this larger clump to be separated, which would allow some of these pieces to be accessed. Third, and probably the most common reason, there may just be too many molecules that need to come together in just the right way all at once for the process to occur in one step. Two molecular collisions are very common, and three molecule collisions happen, but much more rarely. But any reaction in which more than three molecules must come together would certainly happen in more than one step, and even those that require three molecules to collide almost always occur in two steps. Each of the steps of a mechanism is called an elementary reaction or an elementary step. One extremely important characteristic of an elementary step is that the rate expression for the step can be written directly from the reactants of the step. Specifically, the exponents of the concentrations in the rate expression are exactly the coefficients of the substances in the step. For example, suppose an elementary step is H2 plus NO2 gives H2O plus NO. Then the rate expression for that specific step is rate equals K times the concentration of H2 to the first power times the concentration of NO2 to the first power. I want to emphasize that it does not mean that the observed rate expression is that expression. The overall rate expression must still be determined by experiment. However, this is critically important in identifying whether a particular mechanism can explain the observed or experimental rate expression. The number of reactant molecules in an elementary step determines the molecularity of the step. Unimolecular if one molecule reacts, bimolecular if two, whether two different molecules or two of the same molecule, and termolecular if three react. Let's focus on multi-step mechanisms for a bit. There are three important characteristics of these mechanisms. First, one of the steps in the mechanism will be slower than all of the others. The slowest step in a mechanism is called the rate-determining step, since the reaction cannot go faster than its slowest step. By the way, this general principle is applicable to all processes, not just to chemical reactions. Let's suppose we have to put together a test of 10 pages and want to do so by the following steps. Number 1, collect the 10 pages in order. Number 2, straighten the pages. Number 3, staple the pages. Which step would likely be the rate-determining step? Since the straightening and the stapling can happen in less time than the collecting, the most likely slowest step is the first step. We will not be able to produce straightened, stapled tests faster than we can collect the 10 pages. If we want to speed up the process, we need to speed up that step. In a similar way, in order to increase the rate of a chemical reaction, one must increase the rate of the slowest, or rate-determining, step. The second important characteristic of a multi-step mechanism is that the elementary steps must add to give the overall reaction. The mechanism is supposed to show us exactly how the reaction occurs. That is, exactly which molecules react in what order to get us from the reactants to the products. If, when we add the elementary steps, we do not get the overall reaction, then the steps do not take us from the reactants to the products, and the steps cannot be a mechanism for that overall reaction. It is like having directions from your house to your friend's house. We know the starting point and we know the ending point. If we follow the directions starting from your house, but we don't get to your friend's house, then the directions are not very good. Similarly, if we start at the reactants and follow the steps of the mechanism but don't get the products, the mechanism isn't any good. How do we know whether a particular reaction occurs in a single step or by a series of steps? Here are a couple of things to do. First of all, if the order for a particular reactant does not match the coefficient in the overall reaction, the reaction must be occurring in more than one step. If the reaction occurs by a single step, then the overall reaction is the only elementary step in the process, and the rate expression will match the coefficients. Second, if more than two molecules are involved, it almost certainly will occur in more than one step, even if the order matches the coefficients. It is much more likely that a reaction involving 3 or more molecules will occur by several steps than all at once. Let's take a look at an example. A reaction occurs between NO2 and CO, producing NO and CO2. When we determine the rate expression by experiment, we find that the rate expression is rate equals K times the concentration of NO2 squared. That is, the reaction involves carbon monoxide, so CO must be present for the reaction to occur, but the rate of the reaction does not depend on the concentration of carbon monoxide. Therefore, the reaction occurs in more than one step. A proposed mechanism involves 2 steps. Step 1. 2 NO2 molecules collide, creating NO3 and NO. This is a slow step. NO is one of the product molecules, and NO3 is an intermediate. In the second step, the intermediate NO3 reacts with the CO, making CO2 and NO2. This is a fast step. Since the CO is not part of the slow step, its concentration does not affect the rate of the reaction, and it does not appear in the rate expression. Here is the third important point about the multi-step mechanisms. The rate expression for the overall reaction must be the same as the rate expression for the rate-determining elementary step. Let's look at another example. In this case, the reaction is 2NO gas plus Br2 gas gives 2NOBr gas. The experimentally determined rate expression is rate equals K times the concentration of NO squared times the concentration of Br2, a third-order reaction. It is possible that the reaction is a single step, but this rarely happens, so it is more likely to be a 2-step mechanism. proposed mechanism has step 1 as a fast reaction that is an equilibrium. NO plus Br2 gives NOBr2. The second step is slower. NOBr2 plus NO gives 2 NOBr. The rate expression for the overall reaction is the rate expression for the slowest elementary step, which in this case is step 2. The rate expression for that step is rate equals K2 times the concentration of NOBr2 times the concentration of NO. But NOBr2 is an intermediate. How can we know its concentration? The NOBr2 can react in two ways. It can react with NO to form NOBr, that is step 2 of the mechanism. Or it can decompose into NO and Br2, that is the reverse reaction in step 1. The reactants and products in step 1 are in equilibrium with each other, so the rate of the forward reaction is equal to the rate of the reverse reaction. Because the forward reaction for step 1 is an elementary step, its rate expression is rate F equals K1 times the concentration of NO times the concentration of Br2. Similarly, the reverse reaction in step 1 is also an elementary step, so its rate expression is rate R equals K minus 1 times the concentration of NOBr2. Therefore, K1 times the concentration of NO times the concentration of Br2 is equal to K minus 1 times the concentration of NOBr2. If we solve for the concentration of NOBr2, we get K1 over K minus 1 times the concentration of NO times the concentration of Br2 equals the concentration of NOBr2. If we substitute this back into the rate expression, we get the rate equals K2 times K1 over K minus 1 times the concentration of NO times the concentration of Br2 times the concentration of NO, which simplifies to rate equals K times the concentration of NO2 squared times the concentration of Br2, which is the experimentally determined rate expression. So we have confirmed that the rate expression for the proposed mechanism, with a fast equilibrium for the first step and a slow second step, matches the rate expression we determined experimentally.